Well, hello, everybody. Nice to see you. My name is Eugenia Etkina. I'm from Rutgers University. And the title of my short presentation today is When Learning Physics Mirrors Doing Physics. Well, let's start with a picture that you probably all saw. A child eating dirt. Why would children eat dirt? We can approach this question from a physics point of view. And it would look like something like this. So dirt, looks like chocolate. Well, then if it is chocolate, when I eat it, it will taste like chocolate. So this is our testing experiment. If you look at this quick process, you see that that's exactly what physicists do when they discover new ideas. But there's more to this, simple picture and the funny process that I described. If you look at children trying to master tricks on skateboards or bicycles or figure out computer games, you will see amazing skills that they demonstrate. They try and fail again and again and again. They test their ideas experimentally. They persevere, they work together. And they're doing all this because they want to do it. They're motivated. And what we say in education, they have the need to know. So why don't they do it in our classrooms? Well, I don't want to be really controversial, but I will be. I think that the problem is that traditional and even reform teaching goes against much of what we are good at and much of what we know helps people learn. What do I mean? Well, the answers come before questions. We tell students something that they have no need to know yet. Grades, we give them grades for their work. They don't have an opportunity to improve like the kids who are doing tricks on their skateboards or bicycles. So they don't have an opportunity to try without being afraid to fail. We preset the pace of the curriculum. So if you're learning at a different pace, you're punished for it. If the class being graded on a curve, then you're also punished for collaborating with your peers. And if you have traditional problems, and I mean the problems that have one right answer, numerical answer on the multiple choice test, then you punish those who need reasoning tools other than mathematics, and in our physics case is algebra or calculus. And what's important that for women, all these issues are exacerbated due to their tendency to blame themselves and often having an imposter syndrome. So if I feel that I don't belong to this environment, then I will not collaborate with other people, so I will not be a part of a learning community. Well, there's more to it. We teach physics as religion. What do I mean? We tell the students the ultimate truths, and then we'll let them practice it. We tell them this is Newton's second law. This experiment can be explained in this and that way. And then now you go and you apply what I just told you. But we do physics as science. So there is a huge disconnect between the social aspect of how people learn and what actually physics is about when we teach it. So what is the solution? Let me show you an example. We could start with something that everyone experiences, but rarely questions. So, for example, you all observed this, right? Everybody popped a balloon in their lives. The question is, where does this loud sound come from? So, get students in groups. They propose explanations that we call crazy ideas. They discuss stuff with each other and say, okay, maybe the sound is made by air that is coming out of the balloon. How can we test it? Again, the students work in groups and come up usually with an experiment. Well, let's fill the balloon with something other than air. Let's fill it with water. If the air is responsible, then the water will not make a loud sound. And we do it. Well, there is some sound, but not nearly as loud as when the balloon is filled with air. So did we prove that the air was responsible for the loud sound? Well, in physics and in science, one experiment that has the outcome that matches the prediction is not enough to prove that the hypothesis on which the prediction was made is correct. So let's do another experiment. So how else can we test the air? They say, okay, if we just want to test the air, we need to remove the rubber from the picture, right? Because the rubber was also a part of the balloon. So how can we do it? Well, let's put air in something that is not rubber. For example, a shopping bag made of plastic, and then poke it. If air is responsible, then we will hear a loud sound. So let's do the experiment. Oops, that's still the water experiment. Now we are going to do, oops, no sound at all. So now did we disprove the air that we just confirmed with the water? So it looks like that the problem is more complicated. The students go back to their groups and they come up with a new idea. Maybe it is not the air, but the rubber. So then let's just have the rubber and pop it with a needle. If it is just the rubber, it should make the loud sound. Here we go. Just the rubber. Well, there is some sound, but not nearly as loud as when we poke the balloon. So it looks like the air is important, but we don't know how. And the rubber is important, but maybe it is how they work together. So what is different from the balloon when the balloon pops compared to when the shopping bag was popped? The balloon rips apart. So maybe it's how fast the rubber is breaking and letting the air out that is responsible for the sound. How can we test that? The students go back into their groups and they work together and they come up with an idea that we need to take the shopping bag, but in plastic bag, but instead of poking it with a needle, we need to make the air come out fast. So we need to kind of bang it together. So let's do it. So we see a much louder sound. So now we can go and ask more questions. Why did we need to do it? What makes the sound? And the whole unit on the sound is started. And you might say, well, that was easy. What about a more difficult idea? Can we use the same approach that we did for the sound of the ripped balloon? So here is a more difficult idea. So imagine that your students learn kinetic molecular theory. They know that air consists of molecules, that they also learned electricity, magnetism, and electromagnetic induction. They know about conductors and dielectrics. They're familiar with ionization of air. And they also learned wave optics, and they know the electromagnetic wave model of light. So they're now convinced that light phenomena can be explained with an electromagnetic wave model of light. Here, and so for them, light behaves as a wave of alternating electric and magnetic fields. So now they observe the following experiment. So they're familiar with an electroscope. We rub a plastic rod with a felt, and we know it's charged negatively. We touch the electroscope and we see the deflection. So now electroscope, the top of the electroscope, remember it's made of zinc, is charged negatively, as well as the metal holder and the needle. So we shine the visible light, nothing happens. Now we shine UV light, and the electroscope discharges. So the students get into groups and they need to figure out what is the mechanism behind the discharging of the electroscope. And before they learned that electroscope does not discharge by itself because the air is an insulator. So the students get together and usually come up with an idea that UV light ionizes the air that becomes a conductor. And because there are ions and free electrons in the air, and the electroscope is charged negatively, the positive ions surround the electroscope and discharge it. So the air, the ionization of air, is responsible. How can we test this idea? Well, if this idea is correct, then the UV light should discharge a positively charged electroscope. Let's check it out. So now we take a glass rod, and we know that rubbing it with silk causes it to be charged positively. We charge the electroscope positively and shine visible light. We don't expect anything to happen. According to our idea, visible light does not ionize air. And then we take UV light and we shine, and nothing happens. So UV light does not discharge a positively charged electroscope. So we reject our idea, our crazy idea of ionizing air as the reason for the discharge of the negatively charged electroscope. What else can it be? Well, we start thinking, the students start thinking that maybe it wasn't a good explanation, but maybe there's another explanation. Maybe UV light kicks electrons out of the zinc plate. How does it? We can actually hypothesize, because it's made of oscillating electric and magnetic fields, and maybe the electric field transfers energy to the electrons and they leave. Great. A really possible idea. If this idea is correct and we shine light on the neutral electroscope, it should charge positively, right? So let's check it out. So remember, we need the zinc plate to have the same material. We shine UV light, nothing happens. So does it mean that the UV light does not charge a neutral electroscope because our idea is incorrect, or we forgot about something? So let's think about, why didn't the electroscope get charged? So what do we know about the structure of metals? Inside there's a crystal lattice and free electrons. So maybe the UV light did kick out these some of the free electrons, but once the electrons leave the electroscope, it becomes positively charged and attracts the electrons back. So that's why it didn't get charged. So it's not that our main hypothesis or idea was not incorrect. It's that we overlooked the assumption of how to charge an electroscope and what is happening when it gets charged. So if this is correct, then we need to somehow, if we are shining UV light on a neutral electroscope, we need to pull away those electrons that came out. So how can we do it? We need to bring some positively charged object close to our neutral electroscope while it is being illuminated by UV light. So if all our ideas are correct, then in this case, the neutral electroscope should be charged positively after shining UV light on it. Okay, let's check it out. And the students, of course, get nervous because they propose the experiment and they know what should happen if the ideas are correct. And now they're not testing the ideas, they're validating the assumption of why the previous experiment did not work. So we take an electroscope and charge it positively. This will be something that will pull the electrons off the electrons that came out of our neutral electroscope on which the UV light is shining. So see the zinc plate, neutral electroscope, and we have this mesh so you can see what's going on. So now see that positively charged electroscope, we're shining UV light on a neutral electroscope, and it's showing some charge. Whoa. So before the UV light was shining, this electroscope was showing no charge. And now the charge on the positively charged electroscope decreased, and our neutral electroscope acquired a charge. But according to all our reasoning, both should be still charged positively. So how can we test that? Well, what we can do is bring a positively charged rod close to both of them. And so if they're both charged positively, bringing a positively charged rod will show the increase of the charge, even without touching. So let's see if this actually happens. So these are our electroscopes. We separate them, they're charged. And so that's the positively charged object is bringing, oh, the charge increases as we predicted. And here, yes, the charge increases. So the reading increases, the charge doesn't change. So what does that mean? It means that the neutral electroscope got charged by UV light shining on it. And it means that UV light really can kick electrons out of the electroscope. So how does it do it? And why it is important? That's a great question. And that's how we start the exploration of the photoelectric effect. And what I showed you is the process that we follow when we use the investigative science learning environment approach to learning and teaching physics. Every difficult idea that students need to learn or construct in a physics course starts with observational experiments, when they observe something without making any predictions, with an open mind. They identify patterns in these observations and come up with explanations. We call them crazy ideas to reduce the weight of rightness. They don't need to be right at all. In fact, it's better if they turned out to be rejected, because rejection is easier than proof. Every explanation needs to be tested. So they need to design a testing experiment and make prediction, not based on their intuition. We're not testing their intuition, but on the explanation or a model that they just proposed. And if the outcome does not agree with the prediction based on this explanation, it doesn't mean the prediction was wrong. It means that we need to reflect and rethink. We either propose a different explanation, like we did. Instead of the air, we proposed electrons leaving the metal, or we need to check assumptions, just as we did when we saw that the neutral electroscope did not discharge. Or sometimes we say that we didn't have enough data to even propose a model, so we need to conduct more observational experiments. But when the outcome match, we need to conduct more testing experiments, and that's what we did when, remember, we said the air is responsible. We put the water in, it went like we predicted, and we conducted another experiment, and it didn't go the way we predicted. So we need to do more than one testing experiment. And then once we say, okay, we cannot reject this idea, we proceed to application experiments. But there's more to this approach. I don't have time to talk about it today, but when you ask your questions, you're welcome to do it. We have an array of multiple representations that are our reasoning tools, like hammers and saws when we build a house. We have motion diagrams, force diagrams, energy bar charts as tools helping the transition from the language to the algebra or calculus. And what is important, that students work in groups, in small groups, and the groups share their ideas through the whiteboards. They form a learning community, and the students have opportunities to improve their work without punishment. You saw this natural improvement when students are constructing new ideas, but even when they write a lab report, if they do a quiz or homework, they can always resubmit, and whatever grade they receive, this is their final grade, not reduced because it's a second or a third attempt. So the IEL approach is an example of an intentional approach to curriculum design. What does it mean? Intentionality means that the product of knowledge cannot and should not be separated from the means by which it came to be known. And what does that mean? It means that when we're setting up our classroom, we need to think, what does the setup tell the students about what's going on? For example, we want them to read the textbook before they come to class. This is a very strong message that their knowledge of physics will come from the textbook. And what we want our students to, so what intentionalities we want to communicate to our students is one, about what and how students learn. And the second one is how students feel about learning physics. So the first intentionality is based on the idea that if we want students to learn the process of physics, they have to be engaged in this process, right? And the second is that if a person is unhappy doing something, they will not be motivated to do it. So that means that students learn physics by practicing it, and students develop confidence and growth mindset. So where did these intentionalities come from? The first one comes from the history and philosophy of science, observation of physicists, and brain studies. And the second comes from the studies of learning communities, motivation, confidence, and cognitive development. So I'll give you an example of a history of physics that motivates the approach that we just did. Photoelectric effect. You probably remember that it started by an accidental observation of Henry Hertz, who saw that when you have two charged spheres, the spark between them jumps easier if the sunlight is shining on it. If you enclose this in a glass container, then you need the charge much higher for the spark to occur. He said, well, that's an interesting observation, but I have no time to investigate it. So Wilhelm Haurachs conducted experiments similar to what we did with an electroscope and figured out that the sunlight contains a component of UV light that leads to the discharge of a negatively charged electroscope. But he did not investigate the quantitative aspect, so he couldn't make any mathematical models. So this was done by Alexander Stoletov in Russia and Philip Leonard in Germany. So they conducted quantitative observational experiments and tried to come up with explanations using the electromagnetic wave model of light. And of course, as we know, some of the observations could not be explained by electromagnetic wave model of light. So Albert Einstein comes and says, well, let's take Planck's assumption that light is emitted by portions and extend it to the hypothesis that light is absorbed by portions or quanta. And this hypothesis, this explanation, explained all the observations that were conducted before. So Robert Millikan said, well, this cannot be true, and I'm going to show that you're wrong. I'm going to disprove your hypothesis. And so he worked many years trying to disprove Einstein's idea because he knew what it predicts for a certain experiment. And unfortunately, he could not reject it. So he got a Nobel Prize for the failure to reject Einstein's idea. And later, the first multiplier tubes were built based on the idea of the explanation of the photoelectric effect. And now there's probably no device in the world that doesn't use it. So we can put these people on our IEL progression of logical ideas. We also conducted experiments with physicists in real time when they were solving problems that were new to them. It turns out that they follow pretty much the same process. Of course, it's not a linear process at all, as we discussed, but the elements of reasoning and the connections between them, they remain. Cognitive science tells us a few very important things. First, learning is a social process. And that's why IEL students work in groups, coming up with ideas, testing them, and solving problems. Fixed or growth mindset, you probably heard these words, determine how a person will learn and what choices they will make in the process of learning. And So we give our students an opportunity to improve their work, and we encourage them to do it. And that shows them that what they learn today is not the end, that they can do better than that. So it helps develop the growth mindset instead of, well, today you didn't learn this, you're getting a C and we're moving on. But this resubmission, this improvement of their work and our encouragement for them to improve their work is really important because it develops perseverance. And perseverance, as we know, is one of the major predictors of success in life. If we think about students taking our physics courses, very few of them will become professional physicists or doing research in physics. They might only take this one physics course. So what will they take from this physics course? Will they feel that it's connected to real life? Will they feel that they belong? Will they feel that they're good at it? Or they will feel like most people who you meet and they ask you, what do you do? And you say, I teach physics. They say, you must be smart. Why would they say it? Well, because this is the perception of physics as being very difficult and only for brilliant people. So I hope that our approach helps everyone to be welcome and successful in learning physics. A lot of people work on the development of our materials. We have a whole book that describes it. It's called Investigative Science Learning Environment, when learning physics mirrors doing physics, exactly like the title of my short presentation. We also have an algebra-based physics textbook that is used in colleges, universities, AP physics courses in high schools, and any basically high school physics course that can be used. Comes with the active learning guide with activities and the instructor guide, lots of free videos. We also have a website that allows you to download the labs based on this approach and use formative self-assessment rubrics. We have another website with lots of videos and questions that all follow this philosophical approach. We have specific materials completely free for middle school and high school physics. And we have games, that allow you to learn some of the concepts of physics using this approach in a gaming environment. Well, thank you, and prepare your questions. I will be happy to answer them next time we meet. Thank you.